Hi, everybody. It's Professor Mitchell. We are continuing Chapter 9, and today we're going to talk about conduct for a population mean, where the population standard deviation is known. Now, you might recall from the last video that there are two approaches to doing hypothesis tests. One is called the p-value approach, and we'll talk about that in a later video. Today, we're going to talk about the critical value rejection region approach. Here is your standard copyright disclaimer. And this goes along with the assignment on Newton Alta that has that title. In this section are to determine the critical values of a one-mean z-test at a given significance level to define a rejection region, and make a conclusion and interpret the results of a one-mean hypothesis test where the population standard deviation is known using the critical value rejection region approach. So in order to determine the critical value or values of a one-mean hypothesis test, we need to know the z-score that corresponds with the significance level alpha, and whether the hypothesis test is right-tailed, left-tailed, or two-tailed, which is based on really the alternative hypothesis. You can make that determination just from the alternative hypothesis. So I think we talked about this in the last video, but it doesn't hurt to say it again. So it's going to be a right-tailed test if the alternative hypothesis has a greater than sign. It's going to be left-tailed if the alternative hypothesis has a less than sign. And it's going to be two-tailed if the alternative hypothesis has a does not equal sign. So the most common significance levels are 0.1, 0.05, 0.025, 0.01, and 0.005. The common values for z sub alpha that correspond with these significance levels are found in this table. And I think you've seen this table before. Some of these values are at the bottom of table A2. So you can always find them there. Okay, moving on. Okay, the rejection region of a hypothesis test is the set of values for the test statistic which leads to rejecting the null hypothesis. If the test statistic, z sub 0, lies in this area under the curve, then we should reject the null hypothesis. The non-rejection region is the set of values for the test statistic which leads to not rejecting the null hypothesis. If the test statistic lies in that area, then we should not reject the null hypothesis. A right-tailed test, again, where the alternative hypothesis has the form mu is greater than a number, there will be a specific number here. That rejection region looks like this. It is right-tailed. So the range of values that will lead you to reject your null hypothesis are on the right side. And similarly, a left-tailed test where the alternative hypothesis says that mu is less than a specific number, that's going to be on the left side of the curve. All values less than your critical value. And finally, a two-tailed test where the alternative hypothesis says that mu does not equal a specific number is on both sides. So if your calculated test statistic comes out anywhere up here or down here, you will reject your null hypothesis. If it comes out anywhere in here in the white area, you will fail to reject your null hypothesis. All right, so here's a little warm-up example. They want us to determine the critical value or values for a one-mean z-test at the 5% significance level if the hypothesis test is first right-tailed and then two-tailed. All right, so starting with right-tailed, what this is it would cut off the top 5% of your normal distribution. So remember this notation here, Z sub 0.05, that stands for the 95th percentile, or really the exact value that we're looking for. It's the value that cuts off the top 5%. So in that case, the critical value would be 1.645. The rejection region is on the right side because the test is right-tailed. The critical value is positive, so that's something we're going to have to remember when we have our left-tailed test. In a left-tailed test, the critical value is going to be negative. So the area to the right of the z-score is equal to 0.05, and again, our critical value will be 1.645. On the other hand, if your test is two-tailed, your rejection region will still have area equal to 0.05. However, that area will be split between the right side and the left side of the curve. So for a two-tailed hypothesis test, the rejection regions are on the left and the right. Because the test is two-tailed, there will be two critical values. One will be positive, one will be negative, which split the area under the normal curve into a middle 95%. We know that alpha is 0.05, and the area of the rejection region is equal to 0.05. Since that's split between two areas, instead of using z sub alpha, we need to use z sub alpha divided by 2. So our critical value, or one of our critical values in this case, will be z sub 0.025. So think of that as the z-score that cuts off the top 2.5% of the data. So these critical values are going to be, I'll start over here, 1.96 and also negative 1.96. So what that would look like, draw you a little picture. Here is your normal curve. So your rejection region would be up here and also down here. This area here would be 2.5%. This area up here would also be 2.5%. And these two z-scores would be negative 1.96 and, hang on while I find my mouse. Oh, almost got it, almost got it. Nope. Oh. Hold on a second. Sorry, technical difficulties. Every time I've almost got it, I lose it. Okay, I finally found it, and I went ahead and labeled these two z-scores. So here is your negative 1.96, your positive 1.96. So if our calculated test statistic comes out to be anywhere up here, above 1.96, greater than 1.96, or if it comes out to be less than negative 1.96, we will reject our null hypothesis. All right, so here's another example. This would be a good one for you to try if you'd like to pause the video. We want to determine the critical value or values for a one mean z-test at the 10% significance level if the hypothesis test is left-tailed. Since this is a left-tailed test, we know that the rejection region is on the left side. And because the test is left-tailed, the critical value will be negative. We know that alpha is the left of the z-score is equal to 0.10, and we will use the negative of this value. This value here cuts off the top 10%, but because this is a left-tailed test, we need to use the opposite value. So the critical value for a test like this would be negative 1.282. All right, so here are the steps to doing a full hypothesis test using the critical value approach. First, we're going to choose our null hypothesis, which again is denoted H sub 0, and our alternative hypothesis H sub A. We will decide on the significance level alpha. In a statistics class, that value will usually be given. If you're doing statistics in real life, remember that you choose the value alpha based on, alpha is the probability of making a type 1 error. So you need to decide whether a type 1 or a type 2 error would be more serious, which one would be worse. And if you really don't want to make a type 1 error, you would make alpha pretty small, like 0.01. Then you calculate the test statistic, which your book denotes Z sub 0. Find the critical values, which will help you decide whether to reject or fail to reject the null hypothesis. And then this is really important. You want to write a good English sentence that interprets the results of the hypothesis test. In other words, don't just end it by saying reject the null hypothesis or fail to reject the null hypothesis. So you need to write an interpretation of what that means in terms of the actual problem. And of course, we'll do examples. When we've made a decision about the null hypothesis, it's important to write a thoughtful conclusion about the hypotheses in terms of the given problem scenario. So that's what we were just talking about. Now, there are two possibilities for what the original claim is. Sometimes the original claim is the null hypothesis, and sometimes it's the alternative hypothesis. So if the claim is the null hypothesis, then your conclusion should have one of these forms. If the decision is to reject the null hypothesis, then the conclusion is that there is enough evidence to reject that claim. On the other hand, if the decision is to fail to reject the null hypothesis, then the conclusion is that there is not enough evidence to reject the claim. And here I come back to the criminal trial analogy that we talked about in the last video. So when the defendant comes, or when the jury comes back with a verdict, the verdict is either the defendant is guilty, which means the prosecutor proved their case, so that would be like rejecting the null hypothesis, or the jury says the defendant is not guilty, and that doesn't mean that the defendant proved that they were innocent, right? That's not the defendant's job. The defendant doesn't have to do that. The prosecutor has to prove that the defendant is guilty, and either they succeed in doing that or they don't. All right, so the case where they don't succeed in doing that is failing to reject the null hypothesis. There is not enough evidence to reject the claim. And in that analogy, the claim is that the defendant is innocent. On the other hand, if the claim is the alternative hypothesis, then your conclusion would look like one of these. If the decision is to reject the null hypothesis, then the conclusion is that there is enough evidence to support the claim being the alternative hypothesis. However, if the decision is to fail to reject the null hypothesis, then the conclusion is that there is not enough evidence to support the claim. All right, so here is our first actual full example of doing a hypothesis test. Jay claims that he hits a baseball distance of 280 feet or more on average. His sister doesn't believe him. So Jay decides to do a hypothesis test at a 5% significance level. He hits 20 balls and collects the proper statistics, which are that the mean distance hit for those 20 balls was 275 feet, and the population standard deviation sigma is known to be 10 feet. Now, in a later video, we will talk about the more realistic scenario where the population standard deviation is not known. In the meantime, this is a little easier situation to start with. All right, so here's how that testing procedure would go. The null hypothesis is that mu is greater than or equal to 280, so that's J's claim. And the alternative hypothesis is that mu is less than 280. So I want to repeat something I said in the last video, which is that the alternative hypothesis can only contain the symbols less than, greater than, or does not equal. So the alternative hypothesis never ever contains equality. So as soon as I read Jay claims that he hits a baseball 280 feet or more, I knew that that was going to have to be the null hypothesis because that contains equality. 280 feet or more is greater than or equal to 280. Okay, so we will be testing Jay's claim in this problem. The next step, alpha equals 0.05, that was given in the problem, 5% significance level. And now we will calculate our test statistics. So for a claim about a population mean where sigma is known, this is the test statistic. Again, it's called Z sub 0. The sample mean is X bar. The hypothesized population mean is called mu sub 0. All right, so that's the number that will appear in both hypotheses. And the sigma is given to be 10, and the size of the sample is 20. Now, before we go any further, hopefully you have your calculator within reach. I want you to pick up your calculator and put this formula into the calculator and make sure that you get the value 2.23. And I just double check that myself because I have on a few occasions caught these PowerPoints with mistakes in them, and I just realized I hadn't checked that one ahead of time, but that one does work. So the meaning of this test statistic is like this. In a world where Jay actually hits a ball 280 feet, a sample of 20 hits that averages 275 feet would have a z-score of negative 2.236. So it would be about 2.2 standard deviations below the mean, okay? Now there are two possibilities here. Either the mean really is 280 and we just got a relatively, unusually low sample, or the other possibility is if we decide that that's really, unlikely to happen, we could also conclude that the mean is not really 280, it's actually less. Okay? And which of those things will decide depends on the value of alpha. All right, so now the critical value for this test would be negative z sub 0.05, which is negative 1.645. So before we go any further, I think I would like to draw a little picture because I think when I looked at this earlier, I don't remember seeing a picture. I think the picture is really, really helpful. It's just difficult to draw it on the PowerPoint. All right, so here is my critical value, negative 1.645. And because this is a left tail test, that means, sorry. Let's try this again. Okay, negative 1.645. It doesn't have to be pretty, it just has to do the job, right? Okay, so my rejection region is going to be this region here, which means that if I get any calculated test statistic less than or equal to negative 1.645, I'm going to reject my null hypothesis. And in fact, that's exactly what happened, right? Our calculated test statistic came out to negative 2.236, which is in the rejection region. So that's why we are going to reject our null hypothesis. Let me just finish writing that number, because that's going to bug me. Okay, there we go. So now we will conclude whether to reject or not reject the null hypothesis. Sorry, I missed that. Normally that is a subscript 0. They were all like that before I started this, and I fixed all of them, but I missed that one. Okay, so now I think when I click through, it's going to go to the next slide. Okay. This is a left tail test. Oh, there's another one I missed, because H sub A would be J's hitting distance is less than 280. For a left tail test, if the test statistic is less than the critical value, we should reject the null hypothesis. Since Z sub 0 is negative 2.236 and Z sub alpha is negative 1.645, that does land in the rejection region, so we should reject the null hypothesis. Okay. Hypothesis was that J can hit a ball at least 280 feet, or that his average is at least 280 feet. So the interpretation, the good English sentence that you would write at the end of this problem would say something like, at the 5% significance level, there is enough evidence to reject Jay's claim that he hits a baseball a distance of 280 feet or more. In other words, if his average hitting distance is really at least 280, it would be super, super unlikely that in a sample of 20 hits, the average would be 275 feet or less. All right, so unlikely that we decide, the more probable situation is that his overall average hitting distance is not 280, it's actually less. So Jay's sister was right. All right, here's another example. If you would like to try this one, remember these problems do have about 5 steps to them, the way that your book explains it. Suppose a baker claims that her bread height is more than 17 centimeters on average. Several of her customers do not believe her, so the baker decides to do a hypothesis test at a 5% significance level. The people in these problems are really well educated in statistics. To persuade them, she bakes 20 loaves of bread and collects the proper data, which is that the mean height of the 20 loaves of bread is 18 centimeters. Okay, so that is more than 17, but the trick is it more than 17 by enough to say, no, that's not a fluke, her mean is definitely more than 17. And the population standard deviation sigma is known to be 1.5 centimeters. So that test would look like this. All right, now this time, her claim is that her bread height is more than 17 centimeters, not 17 or more, all right? More than 17 means greater than 17. So this time, the claim is the alternative hypothesis. So the alternative hypothesis is that mu is greater than 17, which means the null hypothesis has to be mu is less than or equal to 17. Next, we specify the significance level, which was given, alpha equals 0.05. And the test statistic will look like this. X bar is 18. The hypothesized population mean is 17. And we're going to do 18 minus 17 and then divide by 1.5 over the square root of 20. Okay, and they have really made me paranoid with the mistakes that they had in some of the previous PowerPoints. So I did just check that one, and I got the same thing, that Z sub 0 is 2.981. So again, what that means is that if the mean bread height really was 17 centimeters, a sample of 20 loaves with a mean height of 18 centimeters would be nearly 3 standard deviations above the mean. Okay? So hopefully you understand at this point that 3 standard deviations above the mean is super, super unlikely. Okay. The critical value this time, because it's a right-tailed test, we're looking for the z-score that cuts off the top 5%. We did that example earlier. That z-score is 1.645. So our rejection region will look something like this. Here is the 1.645. I'm going to try something different to label that because it's really a pain trying to write with this thing. Okay, so hopefully this won't drive me too crazy. Here is the 1.645. And then our calculated test statistic lands up here somewhere. And that value is 2.981. So that is clearly within the rejection region. It looks like we're going to reject the null hypothesis. All right, there's another H sub 0 that I missed. I really did fix a lot of these, but there were a few that I missed also. So that should be a subscript 0. Understand that this notation H sub 0 does not represent a number. Please, please, please don't write H sub 0 equals 17 or something like that. It stands for a statement. So you should write it just like this. H sub 0 is the statement mu is less than or equal to 17. Okay. So we are going to reject the null hypothesis. At the 5% significance level, there is enough evidence to support the claim that the mean height is more than 17 centimeters. Since the original claim became the alternative hypothesis, we talk about whether or not there is enough evidence to support it, all right? So it will take you a little bit of practice wording those conclusions the right way. You know, it's just like anything else, you get better at it the more you do it. And that is the end of this video.